The discriminant is another fascinating part of our quadratic formula. Hopefully you already know that if we were to rewrite this as minus b over 2a plus or minus b squared minus 4ac over 2a. So we've got, this is our axis of symmetry here, the minus b over 2a, and then you plus this section to give you the x-intercept and minus to give you the other one. But when we're talking about x-intercepts, it's this thing underneath the square root. That is our discriminant, the b squared minus 4ac. We can see there that clearly underneath the square root, we know that we can't take the square root of a negative number. So if this value, b squared minus 4ac, the discriminant, if it's less than 0, this equation, this solution won't make sense. So we get no x-intercepts or no solutions. If it equals 0, we're going to have minus b over 2a plus 0, that whole thing. So square root of 0, 0 divided by anything is 0, which will be 0, which is the same as minus b on 2a take 0. So we'd get one repeated solution. And then if this is actually greater than 0, then we have two distinct solutions. So minus b over 2a plus whatever this answer is, minus, and minus b over 2a minus that answer. So two different solutions. So let's just summarize that and keep this clear. You might want to write that, make sure you've got that written in your notes. So we've got, let's go for a color change. We've got, so when the discriminant is greater than 0, this is when we can say that we have two real distinct solutions. Or in other words, we have two x-intercepts. It cuts the axis, the x-axis, twice. Now I've just shown a graph that's got a happy face and it's got two x-intercepts like so. Obviously it could be upside down, it could be skinnier. It's just one example of infinitely many. When the discriminant equals 0, that's when we say we've got one repeated solution. Graphically, that can mean when we've got, it's a situation where it's touching the x-axis. If I'm wording this as a question, I can also say that it might be a perfect square. So when we have, let's say that was cutting at alpha, we would have x minus alpha all squared would be, or stick an a out the front there, would be our function when it's a perfect square like so. That's when it's touching the x-axis. So again, look for these key words, these key terms. So if it says cuts the x-axis twice, two x-intercepts, two real distinct solutions, that's code for discriminant is greater than 0. If we use any of these terms, one repeated solution, only one solution, it touches the x-axis or it is a perfect square, that's when we're thinking of the discriminant has to equal 0. And of course the last situation is when the discriminant is less than 0, and that's when we have imaginary solutions, because that's a whole other part of maths. When we take the square root of a negative number, we get imaginary answers. So we get imaginary solutions. In other words, it does not cut the x-axis, no x-intercepts. That's what that would look like. Once again, you know, it could be a sad face going the other way. These are all situations where we're talking about an actual graph. It could be if you're solving for when two graphs intersect. If I've got a quadratic and a linear function, well, when we're talking about the discriminant is greater than 0, that could mean that we are having 2 points of intersection. So that could mean we've got the situation where we've got a quadratic and then we've got the line that cuts it twice. It could be that you've got two quadratics and they intersect twice. What does that mean if it equals 0? Well, that could be when we've got a quadratic and a straight line. It might be that it's touching there, so it's a tangent, it's a crooked line. If it's this situation, it could be that we've got two quadratics and they're just touching, like so. And obviously, if the discriminant is less than 0 and we're solving for when lines intersect. It means they do not intersect at all. So you've got to make sure that you are putting it into perspective with the question that you're doing. Let's get on to a couple of examples with the discriminant. So a typical question with the discriminant, it could be something simple like this, where it's asking, what's the nature of the roots? So instead of actually working out the whole quadratic formula or see if you can factorize, blah, 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 we can just work out our discriminant. So discriminant is b squared minus 4ac. We should know from our work with the quadratic formula that our a in this situation is 3, the b is -2, and the c is 5. So if we pop that into our formula, we get a straight b squared minus 4ac, so minus 2 squared minus 4 times a, which is 3, times 5, so 4 take 60 minus 56. Therefore, we're saying that for this one, there will be no x-intercepts. Because the discriminant is less than 0, no x-intercepts, it will not touch or cut the x-axis. I could go on further and say that I would know that this graph is totally above the x-axis, because from the 3 here, it's a happy face, it's a positive value. Since a is greater than 0, the discriminant saying it does not cut the x-axis, that means it's got to be totally above the graph, above the x-axis. Right, we've got this equation now. This is a slightly, you can see it's pretty similar, except now instead of having the 5 here, the constant, I've said it's m. And the question could be, for what values of m would this have 1 solution, 2 solutions, no solution? So as soon as we hear that, 1 solution, 2 solution, no solution, we're thinking discriminant. So once again, we'll find our discriminant, and we'll say, yes, that's b squared minus 4ac. So minus 2 squared will be 4 minus 4 times 3, but this time our c is m. So we end up with 4 take 12m. Now, if the question was saying, part 1, when will it have 1 solution? So it'll have 1 solution when the discriminant equals 0. Please make sure that you write that down. Putting your information down when you're doing a test question, even in bookwork, just helps you understand, and in a test the marker understand what's going on here, and shows that you know what's going on. So for it to have 1 solution, the discriminant would equal 0, so we're solving 4 take 12m equals 0. 4 goes on the other side, we've got minus 12m equals minus 4. So when m is 1/3, 4 over 12, when it's 1/3, that's when we would have 1 solution. There will be 2 solutions, or it will have 2 x-intercepts when the discriminant is greater than 0. So this is when we've got 4 take 12m is greater than 0. Remember, we treat an inequality the same way that we treat an equal sign, unless we times or divide by negative. And in this case, to get rid of a times -12, we have to divide by -12. And so this is when we need to change the inequality. So because I'm dividing by -12, that becomes m is less than 1/3. So we've got the situation now when m equals 1/3, we would have 1 solution, 1 touches the x-axis. When it is less than 1/3, we're going to have 2 solutions, so 2 x-intercepts, and therefore there will be no solution, and we don't have to work this out and do anything because there's only 1 situation left, would be when the discriminant is less than 0, and that's when m is greater than 1/3. So if I was writing a test question, I could do this, and now I know I could pick any number greater than 1/3. As we said, this proved it here. 5 is greater than 1/3, we got no solution. If I wanted to pick a number, I wanted 2 solutions for this, I wanted you to use the quad formula, then I would pick a number that's less than 1/3. So if I put -1 or -5, you would work that out and it would have 2 x-intercepts. So that's your typical question. Now let's do one a little bit harder. So consider this situation. Got an unknown involved again. We've got a few extra terms. So trick number 1 is for you to make sure that you realize b is not just the first value here, m, that's in front. It's b is the coefficient of x, and because we've got a couple of x's here, we can pull that out as a common factor. And so m plus 2 times x would give me this. If I pulled out x, x times m gives me mx, x times 2 is the 2x. So in this situation, if we're looking at our a, our b, our c, a is 1, b is m plus 2, and c is 4. And when we see a question that's asking us if it's got one solution, two solutions, no solution, discriminant, discriminant, discriminant. Remember, look for the terminology. It could be asking, is it cutting the axis once, twice, not at all? Again, that's code for discriminant. So let's find our discriminant. B squared minus 4ac. So carefully we substitute in here. It's m plus 2 squared minus 4 times 1 times 4. And we expand. M squared plus 4m plus 4. Take 16 equals m squared. Take 4m. Take 12. So we come back to answer our question, when will it have one solution, two solution, etc. Because we've got a squared here, we know that we're going to have up to two solutions. So the first thing we're going to do is solve for when it equals 0. We know that we can factorize this. Let's see, 6 and 2, so minus 6 and m equals 2. So when m equals 6 and m equals minus 2, the discriminant will equal 0. But how do we know when it's going to be greater than 0 for it to have two solutions? We can't just say it's greater than minus 2 and greater than 6. That doesn't make sense if we looked at that on a number line. We can't do that. So we do a sign diagram, which is just a number line. We go minus 2 and 6. And if you look at this, if this shows you clearly why we couldn't just say, oh, it's just greater than, because if it's greater than minus 2 and greater than 6, you're sort of repeating yourself. If we say it's greater than 2, that means, well, 6 is greater than 2, but we're saying when m is 6, the discriminant equals 0. So how can it be greater than 0 and equal to 0 at the same point? Anyway, let's focus on this. We do our number line, it's called a sign diagram. We want to know for what values of m in here, will it be positive or negative? So we pick a number beyond 6. I always go for something quite large, so 10. If I put 10 in here, back in here, 10 takes 6, positive 4, 10 plus 2, positive 12. A positive times a positive gives me a positive answer. Now we pick a number in between minus 2 and 6. 0 would be an obvious one, but again, you could pick any. 1, 2, 3, minus 1, etc. I'm going with 0. 0 takes 6 is minus 6. 0 plus 2 is positive 2. Negative times a positive gives me a minus answer. Keep going. Pick a number less than minus 2. I'm going with minus 10. Minus 10 takes 6 is a negative answer. Minus 10 plus 2 is also a negative. So a negative times a negative gives me a positive. And it is now clear from my sign diagram that we can see the discriminant will equal 0 at 6 and minus 2. But the discriminant will be greater than 0, therefore having two real solutions when m is less than minus 2, so all of this section here, and when m is greater than 6. It will be less than 0, aka no real solutions, imaginary solutions, never cuts the x-axis, for any values in between 6 and minus 2. And so using our notation, we write it like so. So there's the use of the sign diagram. When your discriminant has an m squared or k squared or any unknown squared, it means you can have more than one solution. And let's just try one more. So another similar problem. Let's have a look at this one. We've got x squared plus 4mx plus 24m take 44. And we want to show that this quadratic has a solution for all values of m. So no matter what value for m we choose to put in here, it'll always get a solution. So as soon as it's saying that again, one solution, two solution, no solution, we're thinking discriminant. In this case, look at our a. Our a is 1. our b is the coefficient of x, which is 4m, and this time it's our c that's a little bit longer, so 24m take 44. We work out our discriminant, b squared minus 4ac, which becomes 4m squared. Please note the use of the brackets. If you didn't have brackets, you'd be saying it's just 4m squared, which will be different as you'll see in a minute, minus 4 times a, which is 1, times 24m take 44. So now, because we've used our brackets correctly, 4m squared is 16m squared. 4 fours are 16, m times m is m squared. 4 times 24 is 96. Negative times the negatives, we've got positive 176 here. So like we did before, we want to find out for what values of m will it actually equal 0. So we go about trying to solve for when this equals 0. We pull out our common factor of 16. Remember, always look to see if there's a common factor. Makes our value smaller. We get a bit excited. We think this is going well. Let's factorize just like we did above, and we can do a sign diagram. But what two numbers times together gives me 11, and positive 11, but adds up to be minus 6, and I can't think of any clearly because 11's a prime number. So I could go to my calculator and try and use the quad formula, and what you would find is it says error, no solutions, or imaginary solutions. Now, if we didn't go to the quad formula, we just went to the discriminant. So we're going to work out the discriminant of the discriminant. Sounds crazy, but it's true. So if we look at the discriminant of this one here, we've got minus 6 squared minus 4 times 1 times 11. So we end up with 36 minus 44, which is less than 0. So that's telling us that this will never be equal to 0. So we're then left with two situations. It would either always be positive or it would always be negative. So we pick a value, any value. Let's try again. Let's go with, well, we can go with 0. If m is 0, 0 squared is 0. Take 0 plus 11. That's positive. If you don't think that's a good one to pick, choose another number for m. Any value in here, you will always find that it will be positive. Okay, so it's never going to equal 0. It's always going to be, so the discriminant of f of x, we have just shown, will always be greater than 0. Therefore, no matter what values for m we put in, you will always have two solutions. Hope that made sense. That's probably the hardest, well, not hard in an algebra sense, but just hard to understand. Hope that makes sense to you. So we'll just finish that off by saying, because the discriminant will be greater than 0, it will have two solutions for all values of m. Okay, so just repeat, we worked at the discriminant, we're trying to solve for when it equals 0. This is our discriminant. We're now finding, I guess this is the discriminant of the discriminant, okay? And we prove that this quadratic here, the discriminant, will never equal 0 because it's always going to have an answer less than 0, okay? And then we look and we said, well, if we then go back to here, so because it's saying the discriminant of this will always be less than 0, what is this actual value going to be? And it will always be positive. Okay. Good luck.